Hi everyone, welcome to this presentation about contextual BERT conditioning the language model using a global state. My name is Timo Denk, and this is joint work with Anna Pelletero that was carried out at Zalando in Berlin. Zalando is an online store for fashion, which has more than 30 million active customers in the European Union. And one of the things customers might see when they come to our webpage is outfits. On the left-hand side, you can see one of these outfits consisting of different articles from the fashion store. A problem that we face in reality is that fashion items go out of stock sometimes. And because we don't want to discard the outfit altogether when one of the items goes out of stock, we have the problem that we want to find a replacement. The replacement shouldn't, in that case, you see the shoe is out of stock. The replacement shouldn't just be any black shoe, but should be a shoe that's actually fitting with the remaining articles in the outfit, style-wise. A way to model this problem is to use a language model. You can see the visualization shows a BERT model in which the outfit is being fed at the bottom, and one of the articles is masked out, the shoes, in that case the ones that are out of stock. And the model's task is to predict a distribution over all articles and make a prediction for which article is fitting as a replacement in that outfit. If you train the model on existing outfit data over time, we've seen like it's able to learn the fashion language kind of, so it's able to learn which articles go well with each other and captures this distribution of style. It's very similar to NLP. In NLP, you have vocabulary over all words or word pieces, and in that case, we just have a distribution over all articles that are in stock. There's a little peculiarity to fashion outfits, which is that they don't have an ordering. They can be seen as sets. And since the only way information about the order of the input is injected in the transformer-based models, including BERT, is the positional encoding, we just account for that by removing the positional encoding altogether. So the outfit is being treated as a set. To recap that real quick, the prediction that the model is making is the probability distribution over all articles that we have in stock conditioned on the articles that are in the outfit and not masked out. In this case, the two articles, the one to the left and the one to the right of the masked out item. You can probably imagine that fashion is quite ambiguous, and there's often a number of possible replacements that one could plug into an outfit. Here's an example, 3 different shoes that could probably fit into this outfit. And this ambiguity is something that's inherent to fashion, but we would like to make the predictions personalized so that we pick the elegant shoes if we have a customer who prefers to buy these types of shoes. Maybe we can infer from their purchase history, or pick the urban shoes for customers that have that particular style. So the prediction that we would like to make is, instead of saying we only condition the distribution over all fashion articles that are the output of the model for the masked position, condition it only on the other articles in the outfit. We say we condition it on the other articles in the outfit and additionally the customer and the information we have about the customer. A straightforward way of adopting the previous method with the BERT model to that new requirement is to say we add a new position to the input sequence. The input sequence would then be extended by this customer embedding you can see in the bottom left, which contains a lot of customer features. It's just a vector constructed from customer features. And now the model has this possibility to also attend to that position and make its prediction based on that position and the other items in the outfit. There's one problem with this method, which is that the first level multi-head attention, or in general the multi-head attention in the model, that's the main element that is for information flow between the different positions, is unaware of the fact that the customer embedding is a different modality and has a different semantical meaning in this entire context than the other items in the outfit. This means it uses the same weights to attend to the customer embedding as it attends to the other items in the outfit, and that's suboptimal. There's no architectural inductive bias that tells the model, all right, this is the customer context. You can use it for one thing, for making personalized predictions, and this is the outfit which you have to use for making a style-wise coherent prediction. And this problem is exactly what we're trying to solve by introducing a global state. You can see here a similar visualization, but it's apparent that the customer embedding is now kind of in this separate box, which is labeled as the global state. And the way the transformer the transformer blocks, which the BERT model is composed of, compute their internal representations is now by also accessing the global state, indicated by the dark black arrows. And the previous normal attention that BERT has are the gray arrows. And this is inspired by the graph networks perspective, because it has been shown that BERT and the transformer-based models can be seen as graph networks. And within the graph networks framework, they are lacking that global state. So this was kind of what gave us that idea of adding a global state and then using it for conditioning. So the prediction is still personalized as in the previous example, but now the difference is that we have separate attention for reading from the global state and for doing that intra-sequence attention that the model is normally doing anyway. So we present in the paper 2 different ways of implementing that global state method. The exact mathematical specifics of it, I leave to the audience to read in the paper. Next, I would jump to the empirical evaluation that we have done on an outfits dataset. And here are some characteristics of the dataset. It consists of 380,000 outfits that themselves are composed of 31,000 different articles, and the average outfit length is 5. Each of the samples is from a specific customer who filled out a questionnaire about their style preferences. I'm going to read it out quickly: age, gender, country, preferred brands, colors, styles, no-go types, clothing sizes, pricing preferences, and actually a number of other features. And these features were given to a professional stylist, who then in turn created or assembled an outfit of Zalando articles that was physically shipped to that specific customer. So there is a strong statistical dependence between the outfit that was created, because the stylist created the outfit for that specific customer based on the questionnaire, based on the information that the customer provided. Now, each of these samples we can take the outfit, remove one of the articles from the outfit, and then let the model make the prediction for what article to put there based on the rest of the outfit, and additionally the customer context, the questionnaire information that we embed into a customer vector. The results of that evaluation you can see in this table. First, the different rows are comparing the different methods of adding context. The first one is the baseline, just no context at all. That's kind of a trivial baseline. Then by concatenating the context vector with every input, then the new position, this is the one I visually showed before, where we just extended the sequence by adding a new position. And then the 2 global state methods that we introduced. By adding personalization, we see a relative improvement of 43% over no personalization. And by adding the global state, we see a 16% relative improvement. Now the number of parameters also increases. So in reality, when one wants to use this in a business context, this trade-off needs to be made. How much worth the increase in parameters is, given the improvement in recall. Recall, it's always like how often the model manages to predict the right item at the rank 1 or among the first 250 ranks in the 3rd column. The BERT model itself can process graphs out of the box. What we did is do an architectural modification of the BERT model that allows it to process the nodes in a graph and additionally take a global context, a global state into account, which is also shown in the figure on the left-hand side of the slide. We have empirically validated this method on our proprietary dataset, where we make personalized article replacements. In that case, the nodes in the graph are the articles in an outfit, and the global state is customer information. We believe this contribution enables also NLP use cases, in which case the graph just consists of sentences, of words, and the context could be something like the creation time of that text or the sentiment. You could consider like a spelling correction that is conditioned on the domain in which the text was written. For example, lawyers, they might use different acronyms than computer scientists. So you can have like this context-dependent spelling correction as one potential use case. With that, I would like to thank you for your attention, and I'm Looking forward to seeing all the other contributions at the workshop and discussing them in the poster session. Thank you.